Hello friends, welcome again to the tetrahedron chemistry classes. So in today's class I am going to take another very important reaction which will enhance your skills of organic reaction mechanism. As the topic suggests, what is the name of the topic? Name of the topic is ace your reaction mechanism skills. So this is the combined problem in which you have to use these three reagents, okay, and this is the starting material and four options are given to you and you have to identify the major product. So one thing is quite clear from the question itself. When the question asks, it is you have to select major or the minor product. That means more than one products are forming, right? And whenever there is a possibility of forming more than one product, then the reaction would be a regioselective or stereoselective. Anything can happen, right? What will happen in this case we will see in a later while, okay? And so what is the problem? First of all, see, before solving the problems you need to understand the structures of the reactants and the role of the your reagents, and you have to analyze the product as well, what actually the products are there, and you only then you can only then you will be able to proceed further, okay? So first of all, you see this is the reagent which is given here, and this reagent is what? Here you can see this three-membered ring is there, and one double bond is also present here. And a very special notification is that in this particular question you can see this particular bond, right? You can follow my cursor. This bond is basically your solid wedge. When it is solid wedge, that means it is above the plane. That means certain kind of stereochemistry is involved in that case, right? And you have to use these reagents. First reagent is MCPBA, and solvent is your dichloromethane, and the reaction is happening at the 0 degree centigrade, okay? And after that, first of all, if you when you form first intermediate, then that intermediate would react with the LDA, lithium diisopropyl amide, right? And the solvent is the tetrahydrofuran, okay? And reaction will occur at from a temperature range of minus 78 degrees centigrade to room temperature. RT stands for the room temperature. And in the last step you will use the aqueous solution of the ammonium chloride, and we will also see what is the role of the aqueous solution of the ammonium chloride. And you have been given A, B, C, D, 4 products, and you have to identify these things, okay? So first of all, you should remember the role of the reagent. So first of all, you see my first step in the reaction is like that. So this is the solution I am writing here. I am solving your problem. This is solution, okay? And I am drawing my starting material. My starting material is this one. This is the methyl group. Double bond is connected here, and of course this is your above the plane ring, and this ring is also having the 2-methyl substitution, okay? And in the first step of the reaction you are using, we are using MCPBA, okay? And solvent is your dichloromethane, CH2Cl2, and reaction is happening at 0 degree centigrade. So first of all, you should know what is MCPBA. So in the corner I am giving you the structure and the important functions of the MCPBA. MCPBA is metachloroperbenzoic acid, right? Metachloroperbenzoic acid. That means you need to draw this benzene ring over there and say this is perbenzoic acid. Benzoic acid is COOH, and when peroxy linkage is there, that means one more oxygen is present here, and at the meta position you are having the chlorine. So this is the structure of the metachloroperbenzoic acid, and this is a very important reagent in the organic synthesis. And the various important functions of this is what? First of all, you need to understand this MCPBA is very strong oxidizing agent, right? Okay, and generally it is used in the epoxidation of the alkenes. What it will do? It will do epoxidation of alkene. That means epoxide will form, And another important function of this MCPBA is oxidation of alcohols. Oxidation of alcohols. So I'm writing OH for this one. And then again, you see, if you have the sulfides, okay, then this MCPBA converts sulfide into sulfoxides. Okay, sulfide into sulfoxides, and these are some of the important functions. Okay, so here in that case, in the reagent, you can see you are having the double bond. So that means this MCPBA will epoxide this particular double bond. So we will use this second important function of this MCPBA, epoxidation of the alkene, right? Because alcohol is not there, sulfide is not there, that means other functions are not possible. So we will use this very important function of MCPBA, that is epoxidation of the alkene ring, right? I hope this is quite clear to you, because I need some space. When I need some space, so I have to remove this thing. I hope you have noted down the things. Okay, this is very, very important, right? Whenever you solve the reactions, then you need to understand the functions of the reagents as well. So epoxidation will occur in that case. And how the epoxidation will occur, you see, this is your ring, okay, and here you see the epoxide linkage will form. Okay, this is the epoxide linkage will form. See, for the reaction mechanism, you need to understand the oxygen present in the perbenzoic acid will be supplied to this particular system, and this will form bond. So I'm not drawing the mechanism, complete mechanism. If you want to know how the epoxidation will occur, I'm giving you the link in the description box, and also the link is also flashing on the right top corner, where you can understand the epoxidation of the alkenes with the help of the metachloroperbenzoic acids and many other reagents as well. Right now you need to understand epoxide will form here. And another very important aspect is that, which you should note, this is your ring which is on the above side. So whenever your epoxidation will occur, okay, whenever your epoxidation will occur, so this will actually, it is present at the top position. So your oxygen will not attack from the top position, it will attack from the bottom position. So please remember, your oxygen will attack from the bottom position, and when your when your oxygen attack from the bottom position, that means this bond would be below the plane. So I am writing here, you see, dashed wedge, and in the stereochemistry you all know this dashed band shows the bond below the plane, and this is the bond which is above the plane. So this is the first step of the reaction which you have done. You may wonder that what this CH2Cl2 is doing. It is used as the solvent, in which actually MCPB and this particular reagents completely dissolves. Okay, so there is no specific role of this CH2Cl2 in that case. Only solubility criteria of this CH2Cl2 is there. Now I'll do the second step for this particular reaction, and you know, in the second step what is given here. So in the second step, you see, I'm writing this one, your LDA is given, LDA, and your solvent tetrahydrofuran is here, and your reaction is taking place from -78 degrees centigrade to the room temperature. Okay, now you need to understand what is LDA and what is its role, actually, what its role. So let us take a look of this LDA as well. LDA is lithium diisopropyl amide. Please remember, lithium diisopropyl amide. Okay, so you will put nitrogen here, okay, and then this lithium, and then your isopropyl group. 2 times isopropyl group is there, lithium is positive and nitrogen is negative. Okay, so this is LDA, and please remember, this LDA is very strong base, very strong base. It is quite strong. Its pKa value is somewhere around 36, approximately 36. Okay, so very strong base. And if you know the function of this one, so it actually do the deprotonation, because it is a strong base. It will do the deprotonation. The primary function of this LDA is the deprotonation. I hope you have noted down this function as well. So I'm removing this. Okay, So now deprotonation, from where actually we can do the deprotonation, it is very, very important, right? Now when you do the deprotonation, so you should remember this is actually the methyl group. When this is methyl group, that means 3 hydrogens are here, CH3, CH3 and CH3. Okay. However, other 2 methyl groups are also there, but they are quite far from this one. So there is no point of removing hydrogens from these 2 methyl groups. So I'll remove the hydrogen from this particular methyl group. Okay. Since how the reaction actually occurs in that case, you see I'm writing here. This was your nitrogen and this is your lithium positive, nitrogen negative, and your diisopropyl groups are also there. So I'm writing in that case, right, in that manner actually. So this nitrogen will grab one of the hydrogen, okay, and that double bond will shift here, right, and this bond will break between oxygen and carbon of the ring, and the electron pair will shift over there. So what will happen in the next step? Next step is like that only, this and this. Now this will become double bond and this is your CH2. This is quite clear, guys. You can see here this one of the hydrogen actually is shifted from this CH3 group to this NH group, and this is now CH2 and one of bond is shifting here, so this will become double. So this is the double bond, right? And what will happen then? You see this is my bond, epoxide bond, which have broken now, okay, and the negative charge over there. Why it is getting the negative charge? Because this epoxide linkage breaks down and the electrons shift onto this electronegative oxygen atom, so that's why it is negatively charged. And in the final product, you can, sorry, in this particular intermediate, what you will do, let me draw this like that, okay, these are the 2 methyl groups. So this is the second stage of the reaction, and then you can go for the third step. So what is the third step? So in the third step, what actually we are doing here, so this is my third step. In the third step, you have your NH4Cl, which is in aqueous medium. So what is the meaning of that? It is quite important. Again, you see, when you have the ammonium chloride, okay, NH4Cl, and when you dissolve in water, it is because it is in aqueous state, it will form your ammonium hydroxide and it will form your HCl. HCl being the strong acid, it will actually give the proton. So basically this step is protic workup. This step is protic workup. So what will happen in the protic workup? So the HCl which we have produced here, so this oxygen actually will grab this H positive, and then you will have your final product, and your final product would look like this. I'm drawing here, you can see this is double bond CH2, okay, and then this would be your OH now, and these are the 2 methyls attached on it, okay. So this is your final product. So now you can see here option B is looking the correct answer, okay. So see, in this step I have explained this oxygen from the MCPB is attacking from the bottom side. It may also attack from the top side. So when it attacks on the top side, so this actually OH will be on the above side. That means another stereoisomer will also form. So basically this reaction is the stereoselective reaction, right? This reaction is this step, basically not reaction. The first step is the stereoselective. So I'm writing stereoselective. And what are the stereoselective reactions? Stereoselective reactions are those reactions in which more than one products are formed, and one is major, others are minors, and all these structures are stereoisomers of each other. If you don't know what are the stereoselective reactions, I am giving you the link in the description box, and also the link is flashing on the right top corner. You can understand the things from there again, right? So this, I hope you understood this reaction very well and the role of the different reagents present in it, right? So in the next class I'll meet you with another very important concept. So that's it for today, right? Thank you very much.